There is a quiet moment, far from the warmth of Earth, when a small interstellar visitor passes through our solar neighborhood without ceremony. No blinding light, no violent collision, only a small object drifting by. As if unconcerned with whether anyone is watching, what draws scientific attention is not the object itself, but the thin veil of gas it leaves behind. Within that faint plume are familiar molecules, including some whose names have long been associated with human fear, and yet, in the vastness of space, do those names still carry the same meaning they do on Earth? Tonight, we move slowly into the story behind this quiet interstellar visitor. It carries no legendary or evocative name, only a technical designation that sounds impersonal, almost indifferent, yet marks something unusual. This is not a body born with our solar system. It is a visitor arriving from the open space between the stars. This object is known as 3I, Atlas. It belongs to a growing family of travelers that were not born with our sun, but arrived from the wide spaces between stars, carrying with them the chemistry and memory of other systems. When we notice 3I, Atlas, we do not see it directly as a solid body. What reaches our instruments first is a faint haze, a gentle plume of gas released as light warms its surface. Within that plume, astronomers identify familiar molecules, simple compounds that form naturally wherever cold ice and radiation coexist. Among them is hydrogen cyanide, a small molecule made of carbon, nitrogen, and hydrogen. In laboratories and in human history, this molecule has been associated with danger and toxicity in space. However, it is also ordinary, drifting through interstellar clouds, woven into the raw chemistry that precedes stars, planets, and life itself. It helps to imagine 3I Atlas, not as a weapon or a threat, but as a fragment of frozen geology, shaped long before our species learned to fear certain words. Its motion through the solar system is smooth and predictable, guided by gravity alone. As it travels, it sheds a thin atmosphere that stretches behind it, quickly diluted by the vastness surrounding it. In this environment, scale matters. Space is not a container, but an expanse, and even substances that feel potent on Earth become diffuse and quiet when released into millions of kilometers of emptiness. The name 3I, Atlas itself, carries this sense of calm classification. The letters and numbers do not dramatize the object, they file it. The 3I simply marks it as the third confirmed interstellar object observed passing through our solar system. Following earlier visitors that introduced us to the idea that such encounters are not singular events, Atlas refers to the survey system that first noticed its movement against the background stars, an automated watchfulness that scans the sky without expectation or emotion. There is something reassuring in this bureaucratic naming. It reminds us that this object is not an anomaly beyond comprehension, but part of a category we are learning to recognize. The solar system, once imagined as an isolated island, is now understood as a place occasionally brushed by material from elsewhere in the galaxy. Dust, ice, and stone move between stars more often than we once believed, crossing the dark corridors of interstellar space and briefly entering the light of foreign suns. In this broader view, 3I, Atlas, becomes less a singular event and more a quiet example. It tells us that the boundary between star systems is porous, and that our neighborhood is not sealed off from the rest of the Milky Way. These visitors arrive without intention, shaped by forces that operate over millions of years, long before any observer is present to assign meaning to their chemistry. When space agencies speak about 3I Atlas, their language reflects this perspective. Statements emphasize that the presence of hydrogen cyanide is not considered significant from a safety standpoint. The reasoning is simple and grounded in well-tested physics. Gas released from a small body disperses rapidly under the influence of sunlight and solar wind. Radiation pressure pushes molecules apart, thinning the plume until it blends seamlessly into the surrounding vacuum. What remains is a trace, detectable by sensitive instruments, but not concentrated in any way that would interact meaningfully with planets or life. The word often used in these explanations suggests irrelevance, not as a dismissal of the molecule's identity, but as a description of its behavior at scale. In space, context transforms substance. A compound that is dangerous in a closed room becomes inert when spread across distances that light itself takes time to cross. The models used to describe this process are not speculative. They are the same models that explain comet tails, solar wind interactions, and the gentle erosion of atmospheres at the edges of planets. These models rest on an underlying assumption that has served astronomy well, that small bodies like comets and interstellar fragments are passive. They follow trajectories set by gravity, release material through simple physical processes, and respond predictably to radiation and motion. They do not steer, adjust, or choose. They are not agents, but remnants, shaped by time rather than intention. To hold this assumption is to place 3I Atlas alongside countless other objects that pass through space unnoticed. It becomes comparable to debris drifting after a distant collision, fragments that obey the same laws, whether anyone is watching or not. In this framing, there is no narrative of pursuit or targeting, only motion and dispersion, expansion and fading. There is a useful contrast here, one that exists entirely within human imagination. We understand the difference between a falling stone and a guided projectile, even though both follow physical laws. The distinction lies not in the equations that describe their motion, but in the presence or absence of purpose. In space, everything we observe so far belongs firmly to the first category. Objects move because they must, not because they aim. This distinction matters because it shapes how we interpret signals from beyond our world. When we see chemistry associated with danger on Earth, it is natural for memory and culture to respond. Yet the cosmos is not organized around human history. Molecules form and persist without reference to how we later come to use or fear them. Hydrogen cyanide drifts through cold clouds where no lungs breathe and no life is present to be harmed. It participates quietly in reactions that, elsewhere, may eventually contribute to the emergence of living systems. As we rest with this understanding, the presence of such a molecule in the wake of 3I Atlas loses its emotional charge. It becomes another data point in a long story about chemistry beyond Earth, about the ingredients that circulate between stars. The object continues on its path, its plume thinning, its signature fading into the background. There is no moment of arrival or departure that demands attention. The passage is gradual, almost imperceptible, like a breath dissolving into open air. In this way, 3I Atlas invites us into a rhythm of thought. It reminds us that the universe operates on scales where urgency dissolves, and where meaning emerges not from alarm, but from patience. We can allow the models, the classifications, and the quiet confidence of accumulated observation to carry us forward. The interstellar visitor moves on, and the space it leaves behind returns to stillness, unchanged in any way that matters to life here, yet subtly richer for having been observed at all. Across interplanetary space, there is a steady, invisible movement that rarely asks for attention. From the sun flows a continual stream of charged particles, spreading outward in all directions, filling the solar system with a quiet pressure. This solar wind is not a storm in the dramatic sense, but a constant breath, shaping the space around planets, moons, and small wandering bodies. Alongside it travels the gentle push of sunlight itself, radiation pressure that nudges dust and gas away from whatever releases them. When a comet or interstellar fragment warms as it approaches the inner solar system, these two influences begin their work almost immediately. Gas escapes from the surface, Dust loosens its grip, and both are carried outward, stretched into a long, delicate tail. The process is so familiar that it has become one of the most stable images in astronomy. A bright head, a trailing plume, and a slow dispersal into emptiness. Within this framework, safety emerges not from force, but from dilution. It can help to picture this not as a technical mechanism, but as a scene. Imagine smoke drifting into a vast, open space where air is constantly moving. The smoke exists, and its composition can be identified. Yet it never gathers, never thickens. It thins as it travels, becoming part of the background almost as soon as it appears. In the solar system, the background is immense, and the clearing never stops. This is the core intuition behind the standard safety model applied to comet tails. Within this model, the specific identity of the molecules matters less than their behavior. Whether the gas is water vapor, carbon compounds, or traces of more reactive chemistry, the outcome is the same. The plume is stretched, swept, and scattered until its presence is measurable only by sensitive instruments designed to notice the faintest traces. From this perspective, risk fades naturally, carried away by distance and motion rather than actively neutralized. Distance itself plays a calming role in these assessments, though not always in the way intuition first suggests. When we hear that a small body passes tens of millions of kilometers away, the number feels large, safely beyond reach. Space agencies often rely on this instinctive reaction, knowing that such distances exceed everyday comprehension. Yet comet tails do not respect the same geometry as solid objects. They are not compact spheres, but extended structures that can stretch astonishingly far. History offers quiet reminders of this scale. Some comets have grown tails long enough to span distances comparable to the space between planets. These tails are not dense structures, but elongated veils, becoming thinner the farther they reach. Their length does not imply strength, only persistence under steady forces. Even so, their sheer extent gently challenges the idea that far away automatically means disconnected. Understanding this difference does not disturb the safety model, it refines it. The crucial factor is not whether a tail can reach across vast distances, but how its material is distributed along that reach. In almost all observed cases, the distribution is so diffuse that passing through such a region is more like moving through a faint mist than entering a cloud. The geometry is large, but the substance is light. Our planet has, on several occasions, experienced this directly. At times in the past, Earth has moved through the extended tails of comets without consequence. These passages were not hidden events. They were noticed, recorded, and later understood through careful observation. What accompanied them were subtle atmospheric effects, gentle displays of light, and, at most, an increase in tiny particles burning harmlessly high above the surface. Meteor showers offer a familiar expression of this process. Each streak of light is the end of a grain no larger than a pebble, meeting the upper atmosphere and dissolving into heat. We gather under dark skies to watch these events, not with fear, but with a sense of wonder. The experience itself reinforces a quiet statistical confidence that streams of cometary debris, encountered again and again, have not translated into planetary harm. Over time, these repeated encounters have shaped a reassuring narrative. The solar system has been moving through remnants of cometary material for as long as Earth has existed. The atmosphere acts as a shield, the vastness of space as a filter. From this long record emerges a sense that the system is stable, that unusual chemistry carried by distant visitors is rendered inert by scale alone. This confidence is not careless. It is built on accumulated observation and consistent physical behavior. The models used to describe solar wind interaction, radiation pressure, and tail formation have proven reliable across many different objects and conditions. They predict not only the shape of tails, but their fading, their responsiveness to solar activity, and their ultimate dispersal into the interplanetary medium. Within such a framework, it becomes natural to group comets together as a class of low concern. Attention is reserved for solid bodies on direct collision paths, objects large enough to deliver concentrated energy. Everything else is sorted into a quieter category, one where motion and dilution are assumed to resolve any potential interaction. Gas, in particular, is treated as fleeting, incapable of remaining cohesive long enough to matter. There is comfort in this sorting. It simplifies a complex environment into manageable expectations. Most of the time, it works beautifully, allowing scientists to focus resources where they are most needed. Yet simplicity always carries with it a soft edge, a place where categories blur. Statistics describe what usually happens, not what must happen in every conceivable configuration. The safety model, grounded in majority experience, quietly assumes that future encounters will resemble past ones. It trusts that cometary material will continue to behave as passive debris, responding predictably to solar forces. This assumption has held for centuries of observation, and it remains reasonable. Still, it rests on the idea that all relevant variables have already been sampled by history. As we extend our awareness beyond the familiar population of solar system comets and begin to notice visitors from other star systems, the background grows richer and more varied. Interstellar objects arrive shaped by environments unlike our own, carrying histories written elsewhere in the galaxy. Most of their behavior aligns smoothly with existing models, fitting into patterns we recognize. Yet their presence gently reminds us that our statistical comfort is based on a limited archive. This realization does not introduce urgency or alarm. Instead, it invites a softer attentiveness, a willingness to observe without rushing to conclusions. The standard safety framework remains a steady foundation, effective and grounded. At the same time, it exists within a living scientific process, one that quietly adapts as new kinds of objects pass through our field of view. As we rest with these ideas, the motion of solar wind continues, unbothered by our reflections. Tails form, stretch, and fade. Particles disperse, becoming indistinguishable from the surrounding space. The models hold, the statistics whisper reassurance, and the solar system carries on its slow, balanced rhythm, open to visitors, yet governed by forces that favor calm continuity over sudden change. When we think about how close an object comes to Earth, the mind often reduces the scene to a single line. There is the object, there is our planet, and between them, a minimum distance, as if the encounter could be measured by one simple number. This way of imagining works well for solid bodies, for compact things with clear edges. Yet, a comet's tail does not exist as a point or a line. It occupies volume, shape, and motion all at once, unfolding through space in a way that is more fluid than rigid. As a comet or interstellar visitor moves along its path, its tail does not trail behind like a straight ribbon. It spreads outward, responding to sunlight, rotation, and the changing direction of motion. What forms is less a line and more a gently widening cone, a region of space that is continuously being swept by released material. The important question is not only how close the central body comes, but how this moving cone aligns with the paths of planets that happen to be nearby. A simple image can help the imagination rest here. Picture a stream of water from a rotating shower head. The nozzle may never point directly at you, yet, as it turns, arcs of water can still pass through the space you occupy. The distance to the nozzle tells only part of the story. The motion and spread of the flow complete it. In the same way, the geometry of a comet's tail involves angles, rotation, and time. Not just proximity. This shift from one-dimensional distance to three-dimensional motion changes how we quietly assess encounters. A planet can remain far from the comet's core while still passing through a portion of the tail's extended structure. Such passages are not collisions. They are overlaps. Gentle intersections within a vast and mostly empty medium. The distinction is subtle, yet it invites a more spacious way of picturing what it means for paths to cross in space. History gives us calm examples of just how far these structures can reach. Some comet tails have extended across enormous spans, stretching through regions of space that feel almost unimaginable when translated into everyday scales. One well-studied comet in the late 20th century revealed a tail so long that a spacecraft far from the comet's nucleus still detected its presence. This was not because the tail was dense, but because it was persistent, thinning slowly as it extended outward. To imagine such a tail, it helps to release the idea of solidity. Think instead of a faint, elongated presence, almost invisible, threading its way through interplanetary space. It is not a wall or a wave, but a whisper of matter, spread thinly across distances that planets themselves take months to traverse. Its reach challenges the simple intuition that distance alone guarantees separation. This understanding gently loosens the assumption that if a comet's core remains far away, its influence must be negligible everywhere else. The tail's geometry allows it to brush regions far removed from the nucleus, not as a concentrated mass, but as a diffuse extension. In this way, space becomes layered, with structures overlapping without force or drama, simply because of their shape and motion. Looking more closely, these tails are not uniform, even within themselves. From a distance, they may appear as smooth streaks of light or gas, but detailed observation reveals complexity. A comet's tail behaves more like a branching system than a single stream. Variations in solar wind, rotation of the nucleus, and uneven release of material create filaments, folds, and subtle concentrations within the broader plume. An image drawn from landscapes can be helpful here. From high above, a river delta looks like a single shape spreading into the sea. Yet within it lies a network of channels, eddies, and pockets where water moves differently. Some regions are thin and fast-moving, others slow and gently pooled. A comet's tail shows a similar richness, though on a scale far removed from earthly rivers. This internal structure matters when we think about averages. If we measure the overall density of a tail, the result is almost always reassuringly small, yet averages smooth over variation. Within the tail, there can be regions where material is momentarily more concentrated, simply because of how flows intersect and evolve. These regions are still extremely tenuous by terrestrial standards, but they are not identical everywhere. Understanding this does not introduce alarm. It refines perception. It reminds us that space phenomena often resist simple summaries. They are dynamic, textured, and responsive to changing conditions. Recognizing this complexity allows scientific models to grow more nuanced without losing their grounding in calm observation. The idea of a near encounter without direct contact emerges naturally from this geometry. A planet may pass through a denser filament within a tail while never approaching the solid core. Such an event is neither a collision nor an absence of interaction. It sits in between, defined by overlap rather than impact, by shared space rather than forceful meeting. In these scenarios, what matters most is probability shaped by geometry. Paths, angles, and timing determine whether an overlap occurs at all. And if so, which part of the tail is involved? Most of the time, the overlap is with the faintest regions, the parts that have already been stretched and diluted by solar influence. Occasionally, the intersection may involve a region that is slightly more concentrated, though still vast and diffuse. Thinking in this way moves us beyond a simple yes or no question of contact. It invites a softer inquiry into configurations, into how moving structures can briefly share space without consequence. The language of near encounters becomes one of gradients rather than thresholds, of gentle variations rather than sudden transitions. As we hold this picture, the comet's tail continues its slow dance with sunlight and motion. Filaments form and dissolve, angles shift, and the entire structure drifts onward, always thinning, always changing. Planets follow their own steady paths, sometimes intersecting these extended forms, sometimes passing well clear of them. Each movement unfolds without urgency, governed by predictable forces that favor continuity over surprise. In this quiet geometry, there is room for careful thought without tension. The concept of a near overlap becomes another way of appreciating how space is filled with subtle structures, most of which pass unnoticed because they do not disturb the larger rhythms of planetary life. The tail fades as it stretches, and the paths that cross within it separate again, leaving behind no clear boundary where one ends and another begins. There are moments when the night sky reminds us of its gentler side. At certain times of year, we step outside and look up to see thin streaks of light crossing the darkness. They appear suddenly, glow briefly, and fade without a sound. These are meteor showers. Among the most familiar ways our planet interacts with material from comets. They arrive predictably, quietly, and for most people, beautifully. These displays are the result of Earth moving through streams of fine debris left behind by comets as they travel around the Sun. Over long periods, tiny grains spread along the comet's path, forming loose ribbons of dust. When our planet passes through one of these streams, the grains encounter the upper atmosphere and heat rapidly, glowing for an instant before dissolving completely. Each streak is the end of something very small, transformed into light high above the ground. The experience has become part of human culture. People gather under dark skies, make wishes, and feel a sense of connection to the wider universe. What is happening physically is simple and consistent. The particles are so small that they surrender all their energy long before reaching the surface. The atmosphere absorbs the interaction gently, leaving behind no trace except memory. Over time, this repeated harmlessness builds trust. It teaches us that passing through cometary debris is, in most cases, a quiet and safe event. This pattern forms the lowest rung of our shared experience. Countless encounters, recorded across generations, reinforce the idea that space regularly brushes against Earth without harm. The familiarity of meteor showers becomes a reference point, shaping expectations about all material that originates from comets. In this context, tails and debris streams are associated with beauty, not danger, and with repetition rather than surprise. Yet between the smallest grains and the largest impacts lies a wide and subtle middle ground. Not all objects that meet Earth's atmosphere vanish in silence. Some are larger, carrying more momentum, and behave differently as they enter the air. Most still break apart, fragmenting under stress and heat. But the energy they release can spread outward before it fully dissipates. One such event occurred not long ago, when a rocky body roughly the size of a small building entered the atmosphere and disintegrated high above the surface. It never reached the ground as a single object. Instead, it released its energy in the air, creating a powerful shockwave that traveled outward. Windows shattered, structures trembled, and many people were injured not by the object itself, but by the sudden movement of air and debris around them. This kind of event occupies a quiet gray zone in our understanding. It is not a global catastrophe, nor is it a harmless spectacle. It demonstrates that even without direct impact, concentrated energy can have tangible effects at the surface. The object obeyed known physical laws, and the outcome matched models once the details were understood. Still, It stands as a reminder that interactions with space are not limited to extremes of either beauty or devastation. The importance of such examples lies not in fear, but in nuance. They show that risk does not exist only at the far ends of a spectrum. There are configurations where outcomes are localized yet significant, rare yet real. Over time, these events quietly expand the range of scenarios scientists consider when thinking about objects that cross Earth's path. An even more distant example offers another layer of perspective. In the mid-1990s, a comet that had ventured too close to a massive planet was torn apart by gravitational forces. Instead of a single body, it became a chain of fragments, each following the same path. Over days, these fragments entered the planet's atmosphere one after another, leaving visible marks that lingered for weeks. This event did not threaten Earth, but it was observed in extraordinary detail. It showed clearly that fragmentation can transform one encounter into many. A single object became a sequence of interactions, each releasing energy at a different location, yet all tied to the same origin. It was a vivid demonstration of how structure and timing can multiply effects without changing the underlying physics. The lesson here is not about scale alone, but about pattern. Nature does not always deliver interactions as single points in time and space. Sometimes they arrive as sequences, shaped by forces acting long before the final encounter. In this case, gravity sculpted the outcome, turning one comet into many impacts, each modest on its own, yet collectively memorable. When we place these experiences side by side, a quiet picture emerges. Most of the time, Earth's interactions with cometary material are gentle. Meteor showers pass unnoticed, except by those who choose to watch. Occasionally, larger objects remind us that energy matters, even when contact is indirect. And in rare, well-observed cases elsewhere, fragmentation shows how one source can lead to multiple effects spread across time and space. History, in this sense, offers a limited but meaningful record. It is rich in examples of calm continuity and sparse in examples of disruption. This imbalance can feel reassuring, and often it is. At the same time, it reflects the nature of sampling. Rare configurations appear rarely, not because they are impossible, but because the conditions that produce them are uncommon. Accepting this does not disturb the calm narrative of space. Instead, it deepens it. It allows us to acknowledge that our understanding is shaped by what we have seen, while remaining open to what we have not yet encountered. The absence of frequent severe outcomes does not require us to imagine them vividly. It simply invites patience and careful attention as new kinds of objects enter our awareness. As interstellar visitors become part of that awareness, the archive slowly grows. Each observation adds texture to the record, expanding the range of known behaviors without overturning the foundations built by centuries of study. The universe continues to present mostly quiet interaction, punctuated occasionally by events that refine, rather than overturn, our models. In this broader historical context, experiences with meteor showers, atmospheric airbursts, and distant planetary impacts settle into a shared rhythm. They form a spectrum of interaction, from the nearly invisible to the briefly disruptive, all governed by the same steady laws. There is no sharp boundary between safety and danger, only gradual transitions shaped by size, structure, and timing. Holding this perspective allows the mind to remain at ease. Space does not move with intent or urgency. It unfolds through patterns that repeat far more often than they surprise. Our planet has traveled through streams of debris for as long as it has existed, absorbing light, sound, and motion into its atmosphere, and continuing on its path unchanged in the ways that matter most. The sky above remains vast and patient. Particles arrive, fragments break apart, energy disperses, and traces fade. What remains is a long, quiet history of encounters, most of them gentle enough to pass without notice, all of them part of a larger, continuous flow that carries Earth forward through the Milky Way without pause or demand. Out in the cold spaces between stars, chemistry unfolds without preference or judgment. Simple molecules form where atoms meet under faint radiation, assembling and drifting apart over long stretches of time. Among these molecules is hydrogen cyanide, a small and efficient arrangement of carbon, nitrogen, and hydrogen. It appears often in the universe, detected in dark molecular clouds, in the envelopes of aging stars, and in the thin atmospheres that surround comets as they warm. From a cosmic perspective, hydrogen cyanide is not unusual. It is one of many compact building blocks that nature uses again and again. Radio telescopes tuned to millimeter wavelengths have traced its presence alongside related compounds, revealing a shared chemical vocabulary across distant regions of space. In this setting, hydrogen cyanide loses its emotional weight. It becomes a letter in an alphabet, part of the grammar through which more complex organic molecules can eventually emerge. This dual nature is worth holding gently. The same molecule that participates in prebiotic chemistry, that contributes to the pathways leading toward amino acids and nucleic precursors, also interacts with living systems on Earth in a very different way. Context changes everything. In the vastness of space, hydrogen cyanide drifts as an ingredient. Within the delicate machinery of aerobic life, it behaves as an interruption. Inside the human body, and in many organisms that rely on oxygen, energy production follows a precise sequence. Oxygen is delivered, electrons are transferred, and energy is released in a controlled flow. Hydrogen cyanide interferes quietly with this process. It does not remove oxygen from the air or blood. Instead, it blocks a key step within the cell, preventing oxygen from being used where it matters most. An image can help here, without urgency. Imagine a power plant that still receives fuel, yet has its internal connections interrupted. The fuel arrives. The machinery remains intact, but the current cannot flow. Energy production slows and then pauses, not because resources are absent, but because the pathway has been gently closed. This is the scale at which hydrogen cyanide acts, not violently, but efficiently, at the level of cellular respiration. Because of this mechanism, relatively small increases in concentration can have noticeable effects on organisms that depend on constant oxygen use. This sensitivity does not mean that all exposure is harmful. In daily life, trace amounts of cyanide-related compounds are encountered regularly, in foods, in smoke, in natural metabolic processes. The body has pathways to process and remove them, converting them into less reactive forms over time. What matters is not the presence of the molecule, but how much, how concentrated, and how long. In open environments, hydrogen cyanide disperses, breaks down, and transforms. Within the atmosphere, it does not vanish instantly. It can persist long enough to be carried by winds, spreading thinly across regions before gradually reacting or being removed. This persistence is measured in spans that feel brief on a cosmic clock, yet extended on a human one. Here, the difference between space and atmosphere becomes clear. Outside Earth, solar radiation and the vacuum itself favor rapid dilution. Inside the atmosphere, motion is shaped by layers, currents, and temperature gradients. Air moves horizontally and vertically, sometimes smoothly, sometimes slowly. Molecules introduced into this system can linger, thinning as they travel, rather than disappearing at once. This does not imply inevitability or catastrophe. It simply highlights that the atmosphere is a complex environment, one that behaves differently from open space. Time becomes an important factor, alongside concentration. A substance does not need to be overwhelming everywhere to matter somewhere. Local conditions shape local outcomes. A familiar comparison can make this intuitive. A single grain of salt dissolved in a vast body of water is barely noticeable. The same grain placed into a small volume has a more distinct presence. The total amount has not changed, only the space into which it is distributed. In atmospheric chemistry, similar principles apply. Distribution determines experience. This understanding helps bridge two realities that otherwise seem contradictory. Hydrogen cyanide can be both common in the universe and challenging for certain forms of life. It can participate in the slow assembly of organic complexity while also interrupting biological processes when conditions align in specific ways. Neither role cancels the other. They coexist, separated by scale, environment, and concentration. When we think about cometary sources of such molecules, this duality becomes especially clear. A comet does not carry intent or design. It releases material according to temperature and physics, spreading it into space. The same release can be insignificant in one context and more relevant in another, depending on how and where it disperses. Between harmless trace exposure and overwhelming concentration lies a broad, quiet, middle ground. Most natural encounters fall well within safe margins, diluted by distance and time. Yet the transition from negligible to noticeable is not marked by a sharp boundary. It is a gradient, shaped by flow, accumulation, and persistence. Holding this gradient in mind allows for calm reflection. It avoids extremes of dismissal or alarm. It respects both the resilience and the sensitivity of living systems. It also prepares us to think carefully about scenarios where distribution matters more than totals, where geometry and timing shape outcomes as much as chemistry itself. As we remain with these ideas, the molecule itself remains unchanged. Hydrogen cyanide drifts, reacts, transforms, and fades according to conditions. In space, it is one letter among many, moving quietly through the dark. In the atmosphere, it becomes part of a dynamic system of air and motion. Subject to winds and sunlight, the broader picture remains slow and spacious. Chemistry unfolds without haste. Life responds according to its own thresholds and adaptations. Between them lies a landscape of interaction that is neither simple nor dramatic, but nuanced and gradual, inviting steady observation rather than urgency, and allowing the mind to stay at rest even as complexity quietly reveals itself. It is sometimes helpful to imagine a range of possibilities laid out gently, not as warnings, but as variations within the same physical setting. When we think about a cometary tail that contains hydrogen cyanide, we are not changing the object itself, only the conditions under which it interacts with Earth. Small shifts in structure, timing, and distribution can lead to very different experiences, even when the underlying material remains the same. At the most familiar end of this range lies the scenario we already know well. The tail is thin, its particles are small, and its gases are stretched quickly by motion and sunlight. Earth moves through this region quietly, high above the surface. Tiny grains glow briefly and vanish, adding to a meteor shower that many people may never even notice. Any trace of hydrogen cyanide is diluted to the point where it blends into the natural background, indistinguishable from what already exists in the atmosphere at extremely low levels. This is the world that standard models describe with confidence, where cometary encounters are visually pleasing and physically uneventful. In this setting, everything behaves as expected. The atmosphere does its quiet work. Solar influence continues uninterrupted, and the event passes into memory as a line in an observation log, or perhaps as a night of faint streaks across the sky. The chemistry remains real, but irrelevant in practice, simply because it never gathers in one place for long enough to matter. This baseline scenario anchors our intuition and explains why reassurance has been the default response to most cometary passages. If we move one step along this spectrum, subtle changes begin to appear. The tail still exists primarily as a diffuse structure, but within it are a few larger fragments, pieces that carry more momentum. Most still burn away, but some survive longer as they descend, releasing energy into the air before fully dispersing. The effects are localized. A shock wave ripples outward, windows may break, and people nearby notice a sudden disturbance rather than a silent light show. Alongside this mechanical effect, any chemical content carried by such fragments is released more abruptly and closer to the surface. The scale remains limited. Winds spread the material, and concentrations drop as distance increases. Yet for a brief time and within a confined area, conditions differ from the background. This is no longer a purely aesthetic encounter, but neither is it a global one. It occupies a middle ground, where nature reminds us that size and distribution shape outcomes more than labels do. Continuing further along the range, we encounter scenarios shaped less by isolated fragments and more by concentrated release. Imagine a piece of material large enough to retain its contents until it reaches denser layers of air, where it breaks apart and disperses what it carries over a wider region. The physics is still familiar. Energy causes fragmentation. Fragmentation causes spread. What changes is the density of what is released and the altitude at which it happens. In such a case, the atmosphere becomes not just a shield, but a medium through which material travels for a time before thinning out. The experience on the ground depends on many quiet variables: wind direction, atmospheric layering, and local geography all play roles. Most areas see nothing at all. Some may experience a transient change in air composition that fades as currents mix and move. The total amount involved may still be small on a planetary scale, yet its temporary concentration shapes how it is perceived locally. This part of the spectrum highlights an important idea. Averages describe overall behavior, but localized effects are shaped by peaks rather than means. The same total quantity of material can be harmless when spread thinly, or noticeable when released unevenly. This is not a statement about inevitability, but about sensitivity to configuration. At the far end of this imagined range lies a scenario defined not by randomness, but by arrangement. Here, the question is no longer how natural variation might unfold, but how outcomes would differ if structure and timing were optimized to prolong contact between material and atmosphere. The focus shifts from mass to geometry, from chance to pattern. In this thought experiment, the tail is no longer treated as a passive plume, but as a sequence of releases aligned with Earth's motion. Instead of a brief crossing, there are multiple overlaps. Instead of rapid dilution, there is extended interaction. The same chemistry is present, but the way it meets the atmosphere is altered, allowing concentrations to remain elevated in specific regions for longer periods. Even here, the forces involved remain physical rather than dramatic. Gravity shapes paths, motion sets timing, and the atmosphere responds according to its own dynamics. What changes is efficiency. When release is spread out in time and space to match atmospheric flow, effects that would otherwise be fleeting become more persistent. The difference lies not in the material itself, but in how it is delivered. This distinction between accidental and arranged interaction is subtle, yet significant. Natural encounters favor randomness and dispersion. Designed sequences favor alignment and repetition. Both obey the same laws, but they occupy different places on the spectrum of possibility. Recognizing this does not require alarm. It requires clarity about which assumptions underlie which conclusions. Throughout this entire range, one principle remains constant. The transition from harmless to harmful is not marked by a single threshold. It is gradual, shaped by multiple parameters that interact quietly with one another. Small changes in size, density, timing, or geometry can shift an outcome from one category to another without altering the fundamental nature of the object involved. Holding this spectrum in mind allows for a more flexible understanding of risk. It shows that familiar models are not wrong, but incomplete. They describe the most common cases very well, while leaving room for less common configurations that behave differently. This is not a failure of science, but a reflection of how complex systems behave when many variables are at play. As we rest with these possibilities, it becomes easier to see them as variations on a theme, rather than steps toward inevitability. The universe does not rush from beauty to harm. It explores a wide middle space where most interactions remain gentle, and only specific alignments produce stronger effects. Even then, outcomes are shaped by context, duration, and distribution rather than sheer magnitude. The comet's tail, whether thin or structured, continues to disperse. Winds continue to move air across continents and oceans. Sunlight continues to drive chemical change, breaking down and transforming what is released. The system remains dynamic and responsive, favoring balance over accumulation. In this quiet view, scenarios are not predictions, but perspectives. They help us understand how the same ingredients can lead to different experiences without assigning intent or urgency to the cosmos. The spectrum remains open-ended, fading naturally back into the steady background of space, where motion, dilution, and time continue their slow, patient work, and where even complex possibilities settle gently into the larger rhythm of the Milky Way. Around our planet, there is a kind of invisible architecture that we rarely feel directly. It does not have walls or edges, yet it shapes the motion of charged particles moving through space. Earth's magnetic field extends outward, curving through the region where solar wind flows, forming a protective structure known as the magnetosphere. Within it, certain particles do not simply pass by, they become guided, spiraling along magnetic field lines in looping paths that can persist for long periods. This behavior is one of the quiet signatures of plasma physics. Charged particles moving through a magnetic field experience a force that bends their trajectories. Instead of traveling in straight lines, they follow curved paths, often winding in helical motion as they travel along the invisible lines of the field. Some become trapped between regions of stronger magnetic intensity, bouncing back and forth, held in place not by physical barriers, but by geometry and motion. It can be soothing to imagine this as a kind of invisible bottle, not a rigid container, but a region where particles remain confined, circulating within an unseen corridor. They do not stop, yet they do not escape easily either. This is how Earth's radiation belts form, and why certain regions around our planet contain higher concentrations of energetic particles than the surrounding space. The existence of this natural confinement matters because it shows that space is not always a place of immediate dispersal. Under the right conditions, motion can be guided, held, and structured. A particle's presence can be prolonged simply because it is charged and the field around it is shaped in a particular way. This does not mean that everything becomes trapped. Neutral molecules, with no net charge, move differently. Yet the fact that confinement can happen at all provides a gentle bridge between simple dilution and more complex behaviors. When we turn our attention to cometary tails, we enter a realm where both neutral gas and plasma coexist. A comet tail is not a single substance, but a mixture. Sunlight and solar wind interact with the material released from the nucleus, ionizing a portion of it. Some molecules lose electrons and become ions, joining the plasma environment that is already threaded by magnetic fields carried outward from the sun. In this setting, the tail becomes two overlapping worlds. One part remains mostly neutral, drifting according to gas dynamics, pressure gradients, and the gentle tug of gravity, another part becomes ionized and begins to respond more strongly to electromagnetic forces. These two parts are not separate in a clean way. They interact, exchange energy and particles, and influence one another through collisions and charge transfer processes. The ionized component, in particular, can be shaped by magnetic fields in ways that the neutral component cannot. This is why comet ion tails often appear straighter and more directly aligned with the solar wind, while dust tails curve more gently along the comet's orbit. The plasma follows field lines and flow patterns, creating structures that can look like narrow beams stretching away from the sun. This distinction carries a quiet implication. If a fraction of a molecule like hydrogen cyanide becomes ionized in a cometary environment, that fraction may not disperse purely according to simple gas diffusion. It may be guided, accelerated, or channeled by electromagnetic conditions, lingering in patterns that differ from what a purely neutral cloud would form. This is not a claim of dramatic trapping, but a reminder that multiple mechanisms operate at once. In many cases, the ionized component is swept away quickly by the solar wind. Yet the possibility of partial confinement, or at least partial guidance, exists in principle because we already observe confinement in planetary magnetospheres and structured flow in plasma tails. If we imagine, very gently, a region of space where magnetic geometry slows the spread of ions, we can picture pockets of higher concentration persisting a bit longer than average models might suggest. These pockets would still be tenuous, still subject to mixing and eventual dispersal. Yet they would represent departures from the simplest picture of immediate uniform dilution. Such departures are not surprising in plasma physics. Plasmas naturally form filaments, sheets, and instabilities. They create regions of differing density and temperature, even in environments that appear smooth from far away. Magnetic fields, in turn, can stabilize some structures and shear others apart, shaping where particles collect and where they thin. All of this remains within known physics. It does not require new forces or exceptions to natural law. It requires only the recognition that a comet tail is not just a passive spray of neutral gas, but a dynamic system interacting with electromagnetic fields and flowing plasma. From here, the mind may wonder about the difference between a tail that is purely natural and one that is subtly tuned. This is not a leap into urgency, but an exploration of how control changes outcomes. In our own technology, we already use electromagnetic fields to guide charged particles. Particle accelerators steer beams with magnets. Fusion experiments attempt to confine plasma with carefully shaped fields. These are small-scale demonstrations of a broader principle. Charged matter can be guided without touch. If a sufficiently advanced capability existed to shape electromagnetic conditions around a small body in space, it could, at least in principle, influence the behavior of its ionized plume. The analogy here can remain simple and calm, like adjusting the field around a spray of fine particles so that the stream curves rather than disperses straight outward. The particles are the same. The medium is the same. Yet the pattern changes because the guiding forces are arranged differently. This would not be a matter of breaking physical limits, but of applying them with greater precision than we currently can. It would involve shaping fields locally, creating regions where ionized material is encouraged to remain coherent for longer, or directed along specific paths. The neutral component would still drift and mix, but over time, interactions between the two could allow the guided portion to influence the whole plume's effective structure. Even in this imagined tuning, the environment remains vast and responsive. Nothing stays fixed for long. Solar wind shifts, fields fluctuate, and the system continuously evolves. Any confinement would be partial and temporary, more like a gentle delay than a permanent lock. Yet delays matter in systems where timing and overlap shape interaction. What emerges is a more layered picture of dispersion. Some material spreads immediately, Some follows electromagnetic pathways. Some remains in pockets for a time. The overall tail remains thin and fading. Yet within it, different components respond to different forces. As we hold this layered view, the vastness of the Milky Way remains in the background, steady and quiet. Interstellar space between stars is cold and sparse, yet not empty. Fields thread through it. Particles drift through it, and occasional visitors carry their own small halos of gas and plasma. Near our planet, magnetic lines curve softly, shaping invisible corridors where charged particles linger. Farther away, solar fields stretch outward, guiding cometary ions into long, delicate forms. In these quiet structures, the idea of confinement becomes less like containment and more like choreography. Motion guided rather than stopped. Spread delayed rather than prevented. Patterns forming and dissolving in slow rhythm, always returning toward the same end state of dispersion, yet taking different paths along the way, like faint streams of light moving through a dark, patient sky. There are moments in science when observation moves slightly ahead of explanation. An object appears. Its path is measured, its brightness recorded, and yet something small remains unsettled. Not dramatic, not disruptive, just a faint mismatch between expectation and motion. This is where curiosity usually rests quietly, and where interpretation becomes careful rather than decisive. The interstellar object known as Oumuamua arrived in this quiet space of uncertainty. It passed through the inner solar system quickly, too quickly for prolonged study, leaving behind a trail of measurements rather than answers. Its trajectory followed gravity closely, yet not perfectly. There was a subtle additional acceleration, gentle and persistent, that could not be fully accounted for by the pull of the sun alone. This extra push was not large. It did not resemble propulsion in any conventional sense. There were no flashes, no exhaust plumes, no signals, just a slight deviation, noticeable only because our measurements had become precise enough to reveal it. In the language of physics, it was a small non-gravitational acceleration, the kind that invites explanation without demanding one immediately. One proposal suggested that sunlight itself might be responsible. If an object were extremely thin and broad, light pressure could impart a gentle force, much like wind against a sail. In this view, Oumuamua could have been shaped in a way rarely seen among known asteroids or comets, allowing radiation to influence its motion more strongly than expected. This idea attracted attention not because it was dramatic, but because it fit the data with minimal additional assumptions. At the same time, other explanations emerged. Perhaps the object was releasing gas in a way that was difficult to detect, producing thrust without the usual signs. Perhaps its composition included exotic forms of ice that vaporized without leaving obvious traces. Perhaps its shape was simply unusual enough to confound our intuition, yet still entirely natural. Each suggestion carried its own strangeness, yet remained within the broad envelope of known physics. What mattered was not which explanation one preferred, but how close they all came to the edge of familiarity. Each required conditions that were uncommon among previously observed objects. None were impossible, yet none were comfortably ordinary. The discussion revealed something subtle about scientific reasoning. When faced with an anomaly, the system tends to explore increasingly unusual natural explanations before considering the possibility of deliberate design. This tendency is not born of denial, but of structure. Science is built to work with repeatable processes and testable mechanisms. Intent, by contrast, is difficult to measure directly when the actor is unknown and distant. To invoke it too quickly would require revisiting many assumptions at once, shifting not just one model, but the framework that supports it. As a result, the boundary between natural and artificial becomes softly blurred. An object can behave in a way that feels slightly purposeful, without offering any direct evidence of purpose. The absence of clear markers leaves room for multiple interpretations, none of which can be confirmed decisively with limited data. This situation creates a quiet asymmetry in logic. It is possible to search for signs of intent, to look for patterns, regularities, or signals that stand apart from natural variation. But it is not possible to prove conclusively that intent is absent. One can say only that nothing recognizable has been found within the limits of current observation. An analogy from everyday experience can help settle this gently. Imagine examining a room for hidden devices. One can inspect walls, ceilings, and furniture, and conclude that no devices have been detected. Yet, this conclusion always carries an implicit boundary within the scope of the search, using the available tools. It does not assert that concealment is impossible, only that it has not been observed. In astronomy, this boundary is especially wide. Objects pass quickly, data is sparse, and many properties remain inferred rather than measured directly. When an interstellar visitor displays behavior that is slightly unexpected, the responsible response is not certainty, but humility. The data tells us what happened, not why it happened. This perspective matters because it shapes how future observations are framed. When scientists state that there is no evidence of artificial origin, they are making a precise claim. They are describing the outcome of a search, not issuing a declaration of impossibility. The distinction is subtle, yet important, especially when statements move beyond technical circles into public understanding. Applied to other interstellar objects, this lesson remains relevant. When a new visitor like 3I, Atlas, appears, carrying familiar chemistry yet originating from beyond our system, its behavior is interpreted through the same lens. Models are applied, assumptions are tested, and deviations are examined. If the object fits within known categories, it is treated as natural. If it deviates slightly, new natural explanations are proposed. This process is not flawed. It is cautious by design. It prefers continuity over disruption, explanation over speculation. Yet, it also means that certain questions remain open by default. Intent, if it exists, is not something that can be ruled out in the absolute sense, only constrained by what we can currently observe. In this way, the conversation around Oumuamua serves as a quiet template. It shows how science handles ambiguity, not by rushing to conclusions, but by expanding the range of what is considered plausible within existing laws. It also reveals the limits of that approach, where plausibility stretches without breaking, leaving some interpretations forever just out of reach. This does not imply hidden threats or secret designs. It implies something simpler and calmer. Our tools are powerful, yet finite. Our observations are detailed, yet incomplete. Between what we know and what we can exclude lies a region of indeterminacy, a space where multiple explanations coexist without conflict. Holding this space does not require anxiety. It requires patience. It allows us to speak carefully, to separate what has been measured from what has been inferred, and to accept that some questions remain softly unanswered. The universe does not hurry us toward resolution. It offers phenomena, and we respond with models that evolve slowly over time. As interstellar objects continue to pass through our system, this pattern will repeat. Some will align neatly with expectation. Others will challenge it gently. Each encounter adds texture to our understanding, not by forcing conclusions, but by refining the questions we ask. In this quiet rhythm, uncertainty becomes a stable companion rather than a source of tension. It reminds us that absence of evidence is not evidence of absence, and that confidence in safety or natural origin is always framed by the limits of what has been observed. Science moves forward not by erasing these limits, but by acknowledging them openly and calmly. The stars continue their slow motion across the sky. Visitors come and go, carrying histories we may never fully reconstruct. Our measurements grow more precise, our models more flexible, yet the universe retains its capacity to surprise without alarming. In this balance between knowledge and not knowing, the mind can rest, attentive but untroubled, allowing the unanswered to remain gently unresolved as the larger cosmic flow carries everything onward. Every field of knowledge develops ways to protect itself, not from curiosity, but from overload. Science, in particular, has learned that without boundaries, attention scatters, resources drain away, and meaningful progress slows. Over time, communities of researchers have built quiet filters, standards that help decide which ideas deserve deeper focus and which can be set aside, at least for now. These filters are not dramatic barriers. They are more like internal fire breaks, designed to prevent ungrounded claims from spreading unchecked. Without them, every unusual suggestion would demand equal time, and the signal would dissolve into noise. The firebreak allows the system to stay coherent, to concentrate effort where evidence accumulates steadily rather than erratically. It can be helpful to imagine this process visually. In a large building, firewalls divide space into sections. If a blaze starts in one room, the walls slow its spread, protecting the rest of the structure. Most of the time, this works exactly as intended. Minor incidents are contained, and the building remains safe and functional. Yet the same walls can also slow the movement of heat and light, even when they originate from a legitimate source. This tension sits quietly at the heart of scientific culture. The system is optimized to say no more often than yes. New ideas are expected to climb steep hills of proof before they are allowed to influence mainstream thinking. This protects against error, but it also means that some possibilities remain unexplored longer than they otherwise might. When an idea combines unfamiliar elements or touches sensitive themes, the firebreak tends to activate quickly. Hypotheses that resemble conspiracy narratives, even when built from valid physical components, are often grouped with speculation and dismissed early. This is not necessarily because they are wrong, but because they resemble patterns that have proven unproductive in the past. In this light, suggestions involving interstellar objects as engineered systems or as carriers of non-random risk encounter resistance almost immediately. They cross multiple boundaries at once, touching astronomy, technology, and questions of intent. The protective response is swift, framing such ideas as distractions rather than avenues for careful study. History, however, offers quiet reminders that this dynamic is not always aligned with truth. There have been moments when ideas now considered foundational were once pushed beyond the firebreak. They did not fit prevailing models, and they asked for revisions that felt uncomfortable at the time. Continental drift, the role of microorganisms in disease, and other once controversial concepts all spent long periods outside accepted discourse. These examples are not invitations to accept every novel claim. They are reminders that caution and correctness are not identical. The same structures that guard against error can also delay recognition when reality turns out to be more complex than expected. Progress often arrives not by removing firebreaks, but by slowly strengthening the evidence until the system adjusts its boundaries. This creates a delicate balance. Too little filtering, and science fragments. Too much, and it becomes rigid. The challenge lies in maintaining skepticism without turning it into automatic rejection, especially when dealing with rare or unprecedented phenomena. When we consider interstellar space, this challenge becomes more pronounced. The sample size is small. Each visitor from beyond our system carries unique properties shaped by environments we have never observed directly. Our models are extensions, built from local experience and extrapolated outward. They work well in most cases, but they are not complete maps of all possibility. In such a setting, the question is not whether a particular scenario is likely, but whether it is conceivable within known physics. There is a meaningful difference between improbability and impossibility. The firebreak tends to collapse these categories for efficiency, treating both as reasons to move on. This works well for everyday research, but it leaves edge cases lightly examined. Another layer of complexity appears when we consider the broader cosmic context. If intelligent life arises elsewhere in the galaxy, it will not do so in isolation from error, accident, or conflict. Civilizations, like ecosystems, may leave behind remnants, some functional, some broken, some entirely unintended. Over long timescales, these remnants could drift far from their points of origin. An image from Earth can help the mind settle here. Imagine an ocean crossed by centuries of navigation. Most ships arrive safely. Some sink. Some are abandoned. And a few leave behind hazards that persist long after their crews are gone. A swimmer entering these waters does not need to assume hostility to acknowledge that debris exists. This perspective does not require belief in deliberate threats. It requires only acceptance that the galaxy may contain artifacts and byproducts of processes we do not yet fully understand. In such an environment, risk does not always announce itself clearly. It may appear as an anomaly, a deviation small enough to ignore, yet meaningful enough to deserve attention. The dilemma becomes one of calibration. How do we maintain strong filters against unfounded speculation while remaining receptive to genuinely rare signals? How do we prevent imagination from running ahead of evidence, without allowing evidence to be overlooked because it arrives in an unfamiliar form? Science addresses this dilemma slowly. It refines instruments, expands datasets, and improves models, reducing uncertainty bit by bit. Most anomalies resolve into natural explanations. A few remain open questions, carried forward until better data arrives. The system does not rush, because rushing would amplify error. At the same time, communication plays a crucial role. When scientists say there is no evidence for a claim, they are making a precise statement about current knowledge. When this message passes into public discourse, it can be heard as a declaration of impossibility. The distinction between not observed and cannot exist often blurs outside technical contexts. This blurring contributes to misunderstanding on both sides. Skeptics may feel that caution is being misrepresented as certainty. Others may feel that uncertainty is being inflated into hidden danger. Neither interpretation reflects the calm reality of how scientific boundaries are managed. In the case of interstellar visitors like 3I, ATLSS, this balance is especially delicate. The object can be analyzed with known tools, placed within familiar categories, and treated as natural with good reason. At the same time, the limits of observation mean that some questions remain formally unanswered. This does not invalidate reassurance, but it frames it within a context of conditional knowledge. The purpose of recognizing firebreaks is not to tear them down, but to see them clearly. When we understand why they exist, we can also understand their limitations. We can hold confidence and humility together, trusting established models while remaining aware of their scope. As the galaxy continues its slow circulation, interstellar matter drifts between stars, carrying stories written elsewhere. Most of these stories are quiet, repetitive, and harmless. A few may challenge expectations, not by threatening, but by reminding us that our map of the cosmos is still incomplete. In this gentle awareness, the mind does not need to choose between fear and dismissal. It can rest in a middle space, where skepticism is paired with openness, and where unanswered questions are allowed to remain unanswered for now. The firebreak holds, the building stands, and the vast night beyond continues its calm motion, offering signals at its own unhurried pace. For a long time, the solar wind was imagined as something almost steady, a broad, continuous outflow from the sun, changing slowly with the familiar rhythm of solar cycles, but otherwise smooth enough to be treated with averages. In this picture, space between planets felt like a wide river, flowing in one direction, sometimes faster, sometimes slower, yet rarely surprising. It was a comforting image, and for many purposes, it worked well. This understanding shaped how we thought about anything drifting through interplanetary space. Gas released from comets, dust carried outward, and plasma streaming past planets were all assumed to experience a similar environment. If the wind was broadly uniform, then dispersion would also be uniform. Clouds would stretch, thin, and fade in predictable ways. Safety models were built on this assumption, relying on typical values rather than rare deviations. Within that framework, the idea of rapid dilution felt natural. A comet's tail would be swept outward efficiently, its contents spread thinly across vast distances. Any local concentration would be short-lived, erased by the steady motion of charged particles flowing away from the sun. For decades, this image guided calculations and reassured intuition. As measurements grew more detailed, the picture began to soften. The sun, when observed up close, revealed behavior that was more textured than smooth. The Parker Solar Probe, venturing closer to the sun than any spacecraft before it, carried instruments capable of sensing the fine structure of the solar wind itself. What it encountered was not a simple stream, but a layered, restless environment. Instead of a single flow, Parker detected sharp bends in magnetic field lines, sudden reversals that folded back on themselves like waves breaking upstream. These features, known as switchbacks, appeared frequently, creating regions where particles changed direction abruptly. Alongside them were patches of faster and slower wind interwoven in complex patterns, forming a constantly shifting mosaic rather than a uniform background. In this newer view, the solar wind resembles turbulent water more than a calm river. There are eddies, pockets of relative stillness, and channels of rapid flow existing side by side. Density varies. Magnetic fields twist and reconnect. Energy moves unevenly through space, sometimes stretching material thin, sometimes allowing it to linger. This matters because dispersion depends on environment. A cloud of gas moving through a perfectly uniform flow behaves differently than one passing through a landscape of variations. In regions where the wind is strong and coherent, material is pulled apart quickly. In regions where density drops or flow becomes tangled, motion can slow, allowing structures to persist longer than expected. The idea of density gaps emerges naturally from this complexity. Parker's observations suggest that some regions of the solar wind are less crowded with particles, forming temporary voids or corridors. In these spaces, forces that normally stretch and scatter material may weaken. A cloud passing through such a region could behave differently than one encountering the average conditions assumed by older models. An image from everyday life can help ground this idea. Imagine smoke drifting through a room with multiple fans. Near some fans, the smoke is pulled apart rapidly and disappears. In other corners, where air circulates slowly or not at all, the smoke gathers and lingers. The room as a whole may appear ventilated, yet local pockets tell a more nuanced story. Applied to cometary tails, this means dispersion is not always uniform. One part of the tail may be thinned rapidly, while another part encounters conditions that allow it to remain denser for longer. These differences arise not from unusual chemistry or intent, but from the complex, variable nature of the plasma environment through which the tail moves. This does not overturn the broader understanding that solar wind promotes dilution. It refines it. It suggests that dilution happens unevenly, shaped by structures that evolve and drift over time. Most of the time, these variations average out. Occasionally, they align in ways that produce localized effects distinct from the global picture. For safety models built on averages, this introduces a subtle challenge. predictions remain broadly correct. Yet they may miss edge cases where local conditions diverge from expectations. These cases are not common, but they are not forbidden by physics either. They exist quietly within the variability that Parker has revealed. Recognizing this variability brings the discussion back into the realm of standard physics rather than speculation. No new forces are required. No assumptions about intention are needed. The behavior arises naturally from plasma dynamics, magnetic structure, and flow instability, all of which are now directly observed rather than inferred. As observations grow richer, the task shifts from simplifying to mapping. Instead of asking what the average solar wind does, we begin asking how often and where it behaves differently. This is a more demanding question, one that requires large data sets and careful pattern recognition. Here, new tools enter the scene. Artificial intelligence systems, trained to sift through vast amounts of orbital and observational data, offer a way to notice subtle deviations that human intuition might overlook. These systems do not speculate, they compare, flagging objects whose motion, brightness, or tail structure departs from statistical norms. In this role, AI acts less like a decision maker and more like a quiet sentinel. It scans continuously, marking cases that deserve closer attention without assigning meaning to them. The goal is not to label objects as dangerous or benign, but to recognize when assumptions may not apply cleanly. By combining refined physical models with data-driven detection, science gains a way to respect its own firebreaks while extending its awareness. Instead of lowering standards, it raises sensitivity. Instead of chasing every idea, it listens more carefully to what the data itself suggests. For interstellar visitors, this approach feels especially appropriate. Each arrival is rare, each carries unfamiliar history, and each moves through a solar environment more complex than once imagined. Treating them with calm attentiveness, rather than blanket reassurance or undue alarm, aligns with what Parker has taught us about variability. The solar wind continues to flow, not as a single stream, but as a living system shaped by the sun's surface, magnetic fields, and rotation. Within it, regions of turbulence and quiet coexist, forming a dynamic background through which all small bodies must pass. Cometary tails respond to this background in subtle, shifting ways, sometimes thinning rapidly, sometimes lingering briefly. In this evolving picture, safety is not a fixed declaration, but a continuously updated understanding. It rests on observation, refinement, and humility before complexity. The sun does not behave as a simple source, and space is not an empty corridor. It is an active medium, rich with structure and variation. As Parker continues its journey and AI-assisted analysis deepens, the map grows clearer, not because uncertainty vanishes, but because it becomes better defined. In that clarity, the mind can remain at ease, knowing that complexity does not imply danger, only the need for careful, patient attention as the solar wind carries everything onward through its intricate, quietly shifting flow. When people speak about protecting a planet, the image that usually comes to mind is solid and fast. A large rock on a collision course, a clear trajectory traced across the sky, a countdown measured in years or months. The language is kinetic, built around mass, speed, and energy. In this frame, danger is something that strikes, something that leaves a crater, something that can be mapped precisely before it arrives. Modern planetary defense has grown within this frame. Telescopes scan the sky to measure size and brightness. Orbits are calculated and refined. Probabilities are updated as objects move. The central question is always the same. How much energy would be released if this body were to hit? And where would that energy go? Strategies follow naturally from this question. Nudge the object, break it apart, change its path, just enough so that Earth is no longer in the way. This approach has brought clarity and confidence. It transforms a distant point of light into numbers that can be compared, ranked, and acted upon. The greater the expected impact energy, the higher the priority. Visual maps of risk often reflect this logic, shading regions according to potential damage. From a collision, everything fits into a familiar hierarchy of force. Within such a system, materials that do not arrive as solid masses tend to fade into the background. Gas, dust, and chemistry are treated as secondary features, interesting for understanding composition, but rarely central to questions of defense. If an object is not expected to strike the surface with significant energy, it quietly moves down the list of concern. This is not negligence. It is specialization. The system was built to address a particular class of threat, one that is immediate, visible, and mechanically destructive. Over decades, it has become very good at this task. Yet, its strength also defines its blind spots. It speaks fluently about momentum, but has little vocabulary for dispersed influence. Chemical hazards behave differently from kinetic ones. They do not announce themselves with a single moment of impact. They spread, mix, and accumulate. Their effects can appear gradually, unevenly, and sometimes indirectly. A change may be noticed in statistics rather than in headlines, in patterns rather than in events. An explosion is unmistakable. A slow shift in air composition is not. When harm is distributed across time and geography, connecting cause and effect becomes more difficult. Response systems, which are designed to react to clear incidents with defined locations, can struggle to recognize such diffuse scenarios as single events at all. This difference shapes institutional behavior. Emergency frameworks are often triggered by sharp signals, an impact, a blast, a defined release. When effects are subtle and widespread, responsibility becomes harder to assign. Is it a space issue, an atmospheric issue, a public health issue? Each domain sees only a piece, and none may see the whole clearly enough to act. In such cases, questions of authority become quiet points of uncertainty. If a dispersed cloud of unfamiliar origin were to drift through the upper atmosphere, who would evaluate it first? Who would translate astronomical data into environmental risk? Who would decide whether action was needed? And what kind of action would even make sense? These questions do not have obvious answers, because they sit between established roles. Space agencies focus on tracking objects and predicting motion. Meteorological organizations study weather and airflow. Health systems monitor illness patterns after they appear. The idea of a chemical influence arriving from space does not fit neatly into any one of these structures. This does not mean that such a scenario is likely or imminent. It means that if it were to occur, even in a mild form, existing systems might not recognize it quickly as a unified phenomenon. Signals would be fragmented, interpreted through different lenses, and possibly normalized before they were connected. Seen from this angle, objects like 3i, Atlas, offer something rare and gentle. They provide a chance to think without urgency. An interstellar visitor passes at a safe distance, carries chemistry that is familiar yet unusual, and leaves without consequence. Nothing demands action. Nothing forces a response. The moment remains calm, and yet, precisely because it is calm, it could have been used as a rehearsal, not a drill for evacuation or defense, but a quiet exercise in coordination and thought. How would information flow if chemistry mattered as much as trajectory? How would different disciplines speak to one another? What questions would be asked? And by whom? Instead, the response followed the usual path. Measurements were taken. Statements were issued. Reassurance was offered. And rightly so. Based on current models. The object was categorized, archived, and allowed to pass into the growing catalogue of known interstellar visitors. In doing so, an opportunity remained largely theoretical. The system demonstrated that it could explain why nothing happened, but it did not explore in depth how it would respond if something subtle had happened. This is not a failure. It is a reflection of priorities shaped by past experience. Planetary defense, as it exists today, is excellent at preventing sudden, catastrophic events. It is less practiced at thinking about slow, diffuse influences that do not resemble impact at all. Bridging that gap would require not new alarms, but new conversations, new ways of describing risk that do not rely on force alone. Such conversations can remain calm. They do not need to assume worst cases or hidden dangers. They can begin simply by acknowledging that protection is not only about stopping objects, but also about understanding interactions. Space is not just a place where things fall from, but a medium through which matter and energy move in many forms. In this broader view, defense becomes less about walls and more about awareness, less about reaction and more about integration. It asks how different kinds of data can be held together, how signals from different domains can be compared before they are urgent. 3i. Atlas does not demand that this shift happen now. It does not force a reckoning. Instead, it stands as a quiet example, a case where nothing went wrong, and therefore nothing needed to be done. Such cases are easy to forget. Yet they are often the best moments for learning. As interstellar objects continue to pass through our system, they will arrive with different compositions, different structures, and different contexts. Most will remain uneventful. A few may raise questions that do not fit comfortably into existing categories. Having the ability to notice those questions without rushing to answer them may be as important as any physical intervention. In the end, planetary defense is not a finished system. It evolves with knowledge, technology, and perspective. What it protects against reflects what it has learned to see. Expanding that vision does not weaken it. It makes it more complete. The Earth continues its path around the Sun, wrapped in atmosphere and magnetic field, moving through a galaxy filled with drifting matter. Most of that matter passes without trace. Some of it teaches us something new, not through harm, but through the simple fact of its presence. In this steady motion, there is room to reflect without alarm, to recognize strengths without ignoring gaps, to see visitors like 3i, Atlas not as threats or non-events, but as gentle prompts, reminding us that protection, like understanding, is an ongoing process, unfolding quietly alongside the larger rhythms of space. After all the paths we have followed, it is gentle to return to where we began. An interstellar object, named 3i, Atlas, passing through the solar system, carrying familiar chemistry, observed carefully as it moved on its way. When we look at the data that was gathered, the picture that emerges is steady rather than surprising. Its motion aligns with gravity. Its activity resembles that of an energetic but natural comet. Its tail responds to sunlight and solar wind in ways that fit within known behavior. From this perspective, the simplest explanation remains the most supported. 3i, Atlas, behaves like passive debris, shaped by physical forces rather than guided by purpose. There is no clear sign of control, no unmistakable deviation that demands a new category. When scientists say that there is no evidence of immediate danger, they are speaking honestly within the boundaries of what has been measured and modeled. This does not mean that reassurance is an illusion. It means it is conditional. It rests on instruments, models, and comparisons that have proven reliable many times before. Within those limits, the conclusion that 3i, Atlas, posed no direct threat is reasonable and well-grounded. Science, in this case, is not hiding uncertainty. It is working with it openly. At the same time, there is an important distinction that remains easy to overlook. The absence of evidence is not the same as evidence of absence. Not because something must be hidden, but because observation itself is always partial. Telescopes see what they are designed to see. Models describe what they are built to describe. Anything outside that scope remains undefined rather than disproven. A simple image can help this settle without tension. Imagine a photograph taken in low light. If nothing appears in one corner, it may be because nothing was there, or because the sensor could not capture it. The image does not lie, but it does not tell the whole story either. Its truth is bounded by its resolution. In astronomy, this bounded truth is a familiar companion. Objects arrive briefly, data is incomplete, and interpretation must remain flexible. When scientists state that no intentional behavior has been detected, they are describing the outcome of a search, not closing the door on all possibilities. Precision matters here, not as a hedge, but as an honest reflection of how knowledge works. Seen in this way, 3i Atlas becomes less a verdict and more a lesson. It shows us how conclusions are formed and where their edges lie. It reminds us that confidence and humility can coexist, that one does not cancel the other. We can trust what the data supports, while still recognizing what it cannot yet address. As more interstellar objects are discovered, this balance will become increasingly important. New surveys are already revealing that such visitors are not extraordinarily rare. Over time, many will pass through our system, each with its own structure, chemistry, and history. Most will be unremarkable. A few may challenge our assumptions in small, quiet ways. In that sense, 3i Atlas can be seen as a soft signal rather than a warning, not a threat, and not a false alarm, but a gentle prompt. It invites us to ask whether our models are complete, whether our tools are sensitive enough, and whether our institutions are prepared to think beyond the categories they were designed around. This invitation does not ask for fear or urgency. It asks for readiness. Better models of solar wind variability, more refined ways to track subtle orbital behavior, clearer channels for interdisciplinary interpretation, where astronomy, atmospheric science, and public health can share language before they share responsibility. The object itself has already moved on. Its tail has dispersed. Its presence has faded into the background of the Milky Way, becoming just another entry in a growing archive of interstellar encounters. What remains is not danger, but perspective. The original question that framed this journey does not demand a dramatic answer. Was 3i Atlas an inert projectile or an intelligent one? The most honest response is simple and calm. Based on what we know, it behaved as an inert object. Beyond that, certainty is neither required nor available. And in this case, nothing more needed to happen. What matters more is what we carry forward. Not conclusions about a single visitor, but a way of thinking about visitors yet to come. A habit of asking not only what usually happens, but what could happen at the edges of expectation. A willingness to treat uncertainty as information rather than as a flaw. In this wider view, planetary defense becomes less about predicting every outcome and more about remaining adaptable, less about drawing hard lines between safe and unsafe, and more about understanding gradients. It becomes a living process, evolving alongside observation and insight. The universe does not present its questions all at once. It offers them gradually, through small deviations, unexpected patterns, and moments that feel slightly out of frame. Our task is not to force answers, but to refine how we listen. As Earth continues its quiet journey around the Sun, wrapped in atmosphere and magnetism, interstellar matter will continue to drift past. Most of it will remain silent. Some of it will teach us something new, not by causing harm, but by revealing where our understanding can grow. In that steady motion, there is no need for final judgments, only for continued attention, calm curiosity, and the acceptance that not knowing everything is not a weakness. It is simply the natural state of a civilization that has just begun to notice how wide the cosmic neighborhood truly is. After following the full passage of 3I, Atlas, what remains is not unease, but a rare sense of calm. The object arrived, was observed with care, and then quietly moved on, leaving behind data that fits comfortably within familiar physical laws. Its motion followed gravity, its escaping gases responded to sunlight and the solar wind. There was no clear sign of control, no indication of intention. Science, however, is honest in a very particular way. When it tells us there is no evidence of danger, it is not claiming that every question has been answered. It is simply acknowledging the limits of what we are currently able to observe and measure. Between what is known and what is not yet known, there is always a quiet space where humility and curiosity coexist. Thank you for accompanying us on this slow journey through interstellar space. The universe still holds countless mysteries, unexpected moments, and untold stories moving silently across the night sky. And in the journeys ahead, we will continue to explore them together, without haste, without noise, simply listening to the cosmos in its own gentle rhythm.